Hello, welcome back. Today I am going to start by showing you a few options for the cheating client. Let me change a setting real quick. Alright, I'm going to go to full screen for this so we can see the text a little bit better and show you a few options for how you could have made your clients cheat. Let's make this text a little larger. Anyone who's got trouble with that, let me know. I can always get even bigger. So I'm going to do mostly the low-hanging fruit here, and then I will mention how to do some of the really elaborate ones that I didn't see anybody do, and then I'll leave a few to, maybe the most complicated stuff I'll leave to a later discussion. Maybe we'll come back to this again. So, first of all, where to make the changes. So you could only affect the client, so client was a pretty good place to start. But client doesn't do an awful lot, and a lot of people went and tried to make the changes in something like receive input, which is commented as the bonus because this is where input comes in from the server in order to update the game state. So while you could have done something here, it's sort of really been a bad choice of places to do it because this is where data comes back from the server to update the game state. So if that doesn't happen, then your cheat doesn't happen. That's one problem. The other problem is that this just doesn't relate much to the communication between the client and the server. This is an extra layer on top of that. This is when the server talks back to the client and gives them updates. So I would not have put it there. Some people modified send data itself, but this is such a simple method. All it does is write the output to a line and send it. So it's not particularly complicated, and there's not much we can really do here. Better to figure out where send data is used and modify that area. So if you had looked through the program a bit or just remembered, you'll remember that Grid Game Manager has a lot of the important features. So let's see what Grid Game Manager does in terms of something we could modify. So the client stores a version of the game manager and the server stores a version of the game manager. The client's updates based on that keyframe that it receives from the server, whereas the server updates theirs based on inputs from the client. So actually, again, both ends here, not really something that we can work with. We have the updates, no, what's it called? The receive point method. This is what the server calls in order to receive a point and then map it to the screen. So we can look here and see if there's anything that we can exploit, anything that might not be done correctly. So one thing that you would notice if you look through this is that it doesn't do any kind of boundary checking for size. It just assumes that size is valid, and then it'll make the cursor really, really big. Depending on what the size is, it'll just go larger and larger as I is bigger here. So let's go and see if we can make it so that update cursor can be tricked into updating to a larger size. So first, where does update cursor happen? And again, the serializing stuff, this is all having to do with sending data back to the client, so that's probably not going to be the place we want to look. But let's see, where does update cursor happen? If you looked for it for a bit or just used Eclipse to figure it out, you would see that it's actually in the grid. So in the UI is where we do most of the settings when the user hits the keys and stuff, which makes sense. So color grid contains a lot of the things like the cursor size. One of the challenges is that color grid is shared by both the client and the server. They both actually use this class. They just implement it differently. So the server's version of color grid is this one that just doesn't bind the mouse and keyboard listeners because it doesn't need them. And then the client's version is this one that does bind the mouse and keyboard listeners and also binds a TCP client. So a little bit odd because the server also uses this, but you can still modify it. It would just be that the client is running a different one than the server. But this is actually one semi-decent way to manage a little bit of your anti-cheat. So what you can do is make sure that the client has the same version of the application as you. And one of the ways that you can check for the client having the same version is to, let's say, take the hash of the entire class and see that it matches the hash that you have stored or something along those lines. These are all easily, or not easily, but relatively easily defeated methods, but this is something that a lot of real applications will use as a rudimentary check. They'll just make sure that you're running the same version. So having the same version on the client and the server means the server can check this against its own. The problem, again, is that the client is the one that provides that hash or that copy of the code or whatever, so unless you've gone through a few extra steps in order to make sure that the client has a hard time providing a fake one, well, the client is just going to say that they have the right version when they actually don't. It just puts a little bit more headache on people trying to mess with it. So, first cheat, very easy. Instead of updating the key size legitimately, we are going to send a key size that is not legit. And we are just going to make that the largest that we can, which is 9. We can't do 2 digits because, well, our receiving code, which we'll look at first, I guess. We'll look at it in TCP worker. Our receiving code, when it finds an S, it then extracts the size as the first integer that follows it. So it's a bit of a protection against any attacks that make the cursor even bigger, but it does let us cheat and get it up to size 9. Cheating by making the cursor larger. Let's try that out and see what it does. I'm going to launch a server here. And then I'll launch a client. That's legitimate drawing. And that's my big cheat. Ooh, look at that cursor. You can color the whole screen instantly. Okay. So, got a nice cheat going there. Next, again, I'm going to go back to color grid and look at some other different possibilities there. So I have this send rate that a lot of people looked at, and I set it to 16, which means that something is being sent every 1/16th of a second. Now, some people just made it 1 or 0 or something. I mostly took these, but you know, do the math. That's every 1/1 of a second. That's worse, not better. So you've actually made it slower. But the spirit is there, so I gave it to you if you did that. So you want to make it bigger if you want to reduce or increase the number of messages that are getting sent. So you want something sent no faster than, let's say, 1/1000th of a second. But you know what would be even better is if we just got rid of this altogether. So let's find where it's used. It's used right here as a check if current minus last sent is greater than 1000. So if the amount of time that has elapsed is bigger than the max send rate, then we're going to do this business here. Now this version here, I believe, is bugged. Let me make sure that this is the one that has the bug. Last sent, yeah. So you'll see that last sent never gets updated. So this actually always checks out, so it doesn't actually do anything. So you might have noticed that fixing this didn't really have anything like an impact, right? So what this version really needed in order to not be bugged was one more line in here. And that was to get the time again. Let's see what it looks like when it actually works. So I'm going to run the server and the client again and see what it looks like when it's working. So again, I gave you credit for this if you did it, but the cheat in this case has no impact because the drawing speed limitation actually was broken to begin with. It was bugged. So if you did figure out that it was bugged, it would have given you some credit later when you tried to copy it. So it doesn't work that great for size 1 cursors because it's a little bit too aggressive. It works a little bit better for size 2. So when you went to make the countermeasure for this on the server's end, if you didn't fix the bug, you would find that your drawing was badly done as well. So I'm going to fix it on this end first. Let's change it to, let's say, 32, double the speed. A little better. I mean, at least I can relatively draw, and same here, at least I can relatively draw. Not great, but acceptable. Let's go one more tier up. Let's go to 64. And that's drawable, at least. Pick a different color. 64 is workable. So this will be somewhere around where you would have to configure your server to handle something like 64 as well. So initially bug part, and then again with my cheating, just fill the whole thing up relatively fast. Alright. So the cheating solution here would have either been just don't fix the bug, in which case it remains broken, and you could have just pointed that out. Or, obviously, just comment these two lines out, and then they don't work anymore. So find the matching semicolon there, and then just comment those two lines out. Now there's no more time check, and you've gotten rid of it. Get rid of the send rate notation. Let's mark these. Alright, so the easiest way to send a bunch of points was just to get rid of the containment check, so that every time the mouse was moved it would just send all of the points. And that's fine, that's what a lot of people did. I gave you full credit. I gave you full credit for sending a bunch of points in any way. However, I would say that the best way to send a bunch of points is to send them in a way that is most optimal. So send a bunch of points. First of all, I would think that you would do this continuously rather than when the mouse is dragged. That makes you more likely to win the competition. So where would you put it in order to have it execute continuously when there is no thread here? You would have to probably start your own, right? So I'm going to go ahead and do that. Let's go back to worker and just copy its new runnable code so that I can use it here. I'm going to put that in the client's version of the constructor only, so that only the client has to do this cheating end, and I'll just get rid of all of the stuff inside of here because I want this to go as fast as possible. So I just have my runnable with its while true. Alright, I'm going to recycle some of this stuff. Actually, I'll move the whole sending multiple points thing up there, so I don't need that comment anymore. And I don't want to do a containment check. I don't care about that. I just want to send all the points. But I want to do it in a slightly cleverer way. I don't want to just send each consecutive point, because if I send point 1, and then point 1, and then point 1, I'm not really advancing my drawing much. I want to take advantage of the drawing to the best extent that I can. So I want to use the points in the most optimal manner. So if I can only get through, let's say, 1 in every 20 points, which is probably going to be the case if lots of clients are cheating, I want to use those few points that are getting through in the best way that I can. So what I'm going to do is, instead of counting by ones, I'm going to send every, and since the cursor size is 9, this is kind of guesswork, but I'm going to send about every 8th point. I'm going to send about every 8th point. And let's see if this crashes because of an out of bounds issue. Womp womp. Goodbye. Alright, let's see how I can fix that first. So I haven't instantiated a game here because my game is instantiated in that weird way in the driver, remember? So I saw a few people have trouble moving it out of mouse dragged because they forgot that you need to do, where is that thing? The if game is not equal to null thing whenever you try to use game outside of the classes that run later. Like mouse drag runs late enough that game will be connected, but going back to the driver, you see that game doesn't get connected till last. So if you try to do something in the constructor or something without checking that game is not null, you would get something like that. So if you run into problems there, it's just because of the way that the classes are linked together. And this is a weakness of object-oriented programming in general. It shows that this isn't quite properly designed. We're already starting to do patchwork because of a bit of an oop failure on my part when I designed this. It's that we have these linkages that happen late, and things are null because they haven't been linked yet by the time we reach a constructor. It's not really good news, but it's not terrible news either. It's actually pretty typical of any OOP application. So I'm going to add my if game is not equal to null check here in order to keep it from crashing. Now let's see if we also get out of bounds problems, which we almost assuredly will. Whee! Well, we have some color drawing happening, but we don't have the automatic redrawing of the screen from the cheating version. So what else do we need to do in order to get the cheating up and going here? We'll leave this one for a bit and then talk about the last one, which is to start a bunch of clients that also do the same thing and send all of these points. So once we have this working, we also want to send a bunch of clients that do the same thing, start a bunch of these applications. So what's the easiest way to start a bunch of these clients? There were a few different approaches that I saw. You don't need to start a new color grid for each one. So you could start a bunch of different TCP clients. So you could have done this in a loop or something along those lines and just started a bunch of different TCP clients. You could have gone back to the driver and actually started a bunch of clients here, basically copied the entire client instantiation code, done it a couple times, so even put this in a loop. But then you'd have a few different color grid panels, which you don't necessarily need. And then you also could go back to client and have it start a bunch of different sockets. So you could have it, rather than starting a single socket, start a few, and then begin sending messages into each of those sockets. All of those approaches require you to make an array of sockets or clients or whatever it is that you're doing, and make sure that you tell all of them to update continuously like our color grid is doing here. So I'm not going to go through those solutions because they're a bit long to make the array and everything, but I'll upload it if anybody's interested later. And now let's get into some of the more complicated ones that we might notice. Anybody have an update on what the problem is here yet? And you have any ideas on why this doesn't work? Just for demonstration purposes. Nothing happening, right? Not a single message on the server. Not a single message on the client. So why doesn't that part execute? Why doesn't that part execute? This again goes back to the same game issue. It's actually only the server that gets a version of the game, if I remember correctly. No, the client gets one too, but it goes back to that check, I believe, is that the game doesn't evaluate to non-null. So it was a little bit difficult, again, to get this placed properly. What can I do in order to get it to work at this point? works down here, doesn't it? Alright, we'll go on to the next thing. If anyone comes up with it, we'll circle back. Otherwise, I'll just upload it. So if you wanted to really get yourself to the top of the competitive version, so if you wanted to win in class 1, one of the things I think you had to do was send your color repeatedly in order to make sure. Let's see, someone said to make a button that makes a thread that sends points. Yeah, you could do it on a button, but then again, you're not as fast as you could be. You really do want it to start in the constructor so you can be as fast as possible if you're trying to be competitive about the cheating. So how can I get it to work here in the constructor? Alright, so if you want to be competitive, you also have to send your color repeatedly and the chance that your color gets buried. So you have to go back to the picker panel and make sure that the color was being transmitted repeatedly. So whatever the picker panel does in order to transmit the color, you have to do that same thing several times. So one of the easier ways to do it was to just put a loop around this send color data so that it would be sent repeatedly. Or you could go through and try to link it to a different class. So the red, green, and blue fields are not accessible here, but I think you can look at the color. Yeah, the color is public, so it is still possible to send these, for example, from your color grid portion here. So I would say send it once for every time you try to redraw the entire screen. Now you do have a link to the picker panel somewhere, but not here. So you would either have to provide one, or you would have to figure out some other place where you can do this send data of the RGB. So this was again another relatively difficult addition that you had to make just because the object-oriented part of this is such a fail. Alright, the other thing that you probably had to do was send your size repeatedly, not just once. So again, this is probably going to get lost in the stream of other people's traffic if the server is being attacked by multiple cheaters. So in order to win this part, you would also have to send this repeatedly. And again, the easiest way is just to put it in a loop to make sure that it gets sent repeatedly. Or, again, put it outside of the key being sent. In this case, that's a lot easier. You can just put it right on up here, and I'll leave the color in there actually. Of course, comment it out. So you would have had to get that working as well. Now for the more nefarious ones, you can't quite do them in Java, but one of the things to note is that the worker, when it updates your color, it doesn't do any kind of checking to make sure that it actually got it from any particular source. So if you were very nefarious, you could craft a packet that looks like it comes from one of the other connected people and changes their color to yours. So that would be one of the coolest attacks, but again, very difficult to do because we haven't seen how to craft those kinds of customized packets yet. And besides that, I guess I will leave the others for later because I want to get to our slides today. If there's any questions, let me know. Otherwise, I will just upload the fixed version with all of those things linked together after class here. Alright, let's go on to the slides, see where we left off. Left off at HTTP. We were almost done with it. We looked at these different error messages, and then I introduced Telnet as a way that you can play with HTTP. Telnet is a very old text messaging app, one of the oldest, older than even AOL Instant Messenger. It is the original text messaging app alongside with IRC and Usenet. That was what people used in the 90s and earlier to speak to each other on the internet, just to send text. And it ran over TCP port 23 by default, but it actually is so old that it predates the invention of TCP, so it ran over something else before that. But now we consider 23 to be the Telnet port. It can run on other ports to send arbitrary text of your choice to some destination, which means that if you'd like, you can use it to play with HTTP. It still comes with Windows, surprisingly, as a legacy feature, even though it hasn't been really used by anyone in a long time. You can turn it back on by going to Control Panel, Programs, turn Windows features on or off, and here you'll see a list of quite a few legacy features. One of those is Telnet. You can turn it on there. It doesn't really do anything to have it on. If you want to play with it, go ahead, but you don't have to. I'm sure most people aren't interested, but it is a cool legacy app. Once you have it installed, you can open a command prompt or a PowerShell and type telnet. And you can open a connection by typing open and then the website's name and the port that you would like to use. So in this case, 80. So you can use this to connect to any HTTP website. So go in your browser, find an HTTP site that you want to connect to, start your telnet session in command prompt, and then do open the URL and a space and then 80. Alternatively, you can skip the first command where you open telnet and go directly into open by typing telnet, the URL, and 80. But HTTP doesn't feed any output back to you, so all you're going to see at this point is a blank screen. Once you've opened that TCP connection, which is what Telnet will do for you at that point, you'll just see blank screen nothingness. And then in that blank screen nothingness, you're not going to see yourself typing probably, but you can type things like get with a slash or get slash index.html, and it will actually fetch the web page for you and display it to your command prompt. So this is a way that you can see HTTP working without having to do the complicated work of actually configuring a browser. So if you want to try that out, just to see some HTTP responses coming back to you, give it a whirl. We're not going to do it because it's not that interesting. You can also use Telnet to send each other messages, right? You can connect to somebody else's IP and send messages back and forth that way. So try that out too. It's the messaging application of the future, provided that you're both able to do port forwarding and all of that business. Okay, so let's look at how the HTTP message is actually formatted. What would you actually get when you make an HTTP request? So it has quite a few headers. We've seen a lot of headers already on TCP, on UDP, on all of the layers before, but HTTP takes it to another level. It's got tons of headers. In fact, it's got so many headers, we're not even going to cover all the headers that it's got. First, it's got the status line, where we saw some of those codes last time. It also includes the version, because HTTP has gone through a few. And then, of course, that phrase. But it's really verbose. It actually sends that whole string. It sends HTTP 1.2, the code, so 200, and OK. If it sends a 404, it actually sends the whole phrase. File not found, which is a bit inefficient if you think about it and send a long string like that, but that's what it is. Then it sends you some of the other header lines, which we're just going to go over the important ones here. It's got connection. Connection, you can send something like close. That indicates that the TCP connection is about to get closed. Woo, sorry. You could send the date. That's the timestamp of when this message came in. Useful for the browser to determine some stuff that we're going to look at real soon here. Then you can send the server or user agent. This is a really important one because it provides the information about what browser you're using, and websites, depending on what browser you're using, will send you different versions. The simplest example of this is that if you provide a mobile OS and a mobile browser signature, you're going to get the mobile version of the website. If you provide a desktop operating system and a desktop browser signature, you're going to get the desktop version. But there's also often differences between the Chrome, Firefox, and formerly Internet Explorer versions of different websites just because of different compatibility issues. And then there are differences in how the website treats you depending on what version of the browser you have. So if you have a very outdated version of Internet Explorer, you're probably going to get a different page than if you have a new one. So this is a very important one indeed. It's also where some of the biggest craziness has happened. Because browsers have been around for such a long time, the user agent is now a bunch of nonsense gobbledygook that references browsers that don't even exist anymore. So you will see various user agents for modern browsers containing strings like Gecko and Netscape and all these browsers that don't exist anymore because they are pretending to be newer versions of very old browsers It's a very complicated system, the fact that they have these bizarre user agent strings. So we'll probably look at a few user agent strings when we're done here, just so you can see how weird some of them are. Last modified is a field that's going to use that timestamp too. It's when the last requested object was changed. We're going to see how this comes into play later. You get your content length, that's pretty straightforward, the size of the actual payload, so we see another basically length type header, as we've seen on all of the other layers. So altogether, we've wasted a lot of overhead, if you think about it, on putting a length field on something like 4 different layers. But again, each layer needs to function completely independently. That's that concept of encapsulation. So each layer that requires length in order to function must have its own length field and can't rely on, let's say, the TCP's length field. You've got your content type. This tells you whether you're getting an HTML file, an image, something else, and many, many others depending on the kind of request. Then you get a blank line to indicate the end of your header. So if there's anything that's a waste of internet bandwidth, it's sending a big blank, right? But we did the same thing. We send those -r-n messages to indicate a new line. This is basically just 2 -r-n's, an enter and another enter to indicate that the headers have ended and now the payload begins. So they actually use the same kind of delimiter that we used in several of our programs in order to get stuff working. You had your bonus in the UTF text sender to get things to display on multiple lines. You had to send some kind of delimiting character to do so. HTTP does almost exactly the same thing. It sends a blank line as a delimiter between the headers and the payload. So you've already done some things in the acceptable way of the 70s. Then you've also got your delicious cookies to be concerned about. Most of us have heard the term cookie when we're browsing the internet. We know it has something to do with things that are stored on our machine. But let's talk about what cookies really are. Cookies are used when the server wants to store a little bit of data on your machine so that you can be better served next time you connect to that internet service. HTTP allows you to store that tiny amount of data using cookies. These are very small files that are stored in your browser's cache usually. So each of your browsers, whether you have Firefox or Chrome or Edge, will have its own little cookie cache, and they typically don't share with other browsers, but you can typically sync them up. When you first install Chrome and it asks you, do you want to import your settings from other browsers, it'll try to get your cookies too. Cookies are actually sent in the header, though, which shows you, again, how important HTTP headers are. In fact, the headers are so important that with cookies combined together, you can have headers that are so big that they don't fit into a single TCP segment. And the headers actually have to go over several segments, or the header and the payload have to go over several segments. The simplest example of a cookie is a header with the line set cookie and then the cookie ID, and that's it. And that's all your browser saves, is that cookie ID and then the web page that it corresponds to. Clients will send the cookie back to the server when they connect to it later. So next time you visit that web page, your browser will consult its box of cookies. It will see, do I have a cookie for this page? And if I do, I'm going to go ahead and provide it. And then the server can now identify what you are doing based on the cookie that it receives and proceed from there. So you basically have to encode all of your different website states in these little cookie fields, and these little, you can call them strings, basically. So you have to encode all the different states your website accepts into different cookies as strings, receive those, and then basically branch out and determine which version of the website the person should get based on the cookies that they've provided for you. So a simple example, client visits balloons.com. They want to buy some party balloons, some helium, all sorts of balloon supplies. And while they're on balloons.com, they find the one they want, they add it to their cart. You don't want their cart to disappear next time they visit balloons.com or when they navigate to a different page. So you want to set a cookie for their cart so that you can remember, so the client can render properly what they've got in there. So the server responds with the set cookie bal1. So the cookies field is called bal1 to indicate that they have one bal in their cart, one balloon in their cart. Let's say balloons.com only sells one kind. So the client turns off their computer, leaves, comes back the next day, and they connect to balloons.com again. When they make a request to balloons.com, their browser will also include the cookie, bal1, and the server will respond accordingly and send them a version of the website that shows that they have their cart with one balloon in it. This is much better than the alternative, which would be the server maintaining the state for every user. So the server could easily, based on IP address and port, maybe serve you the same page. Now your incoming port is going to change next time you connect, so that's not going to work. Your IP might be shared by other folks that are using the same NAT as you, so that's not going to work. But okay, let's say we could still identify some way to record individual users without using cookies. Well, then we have to hang on to that information, what, indefinitely? Because if the user leaves their computer and comes back the next day, the server is still hanging on to their cart information. That would become very, very burdensome very quickly. So cookies avoid all of those problems by putting that on the client's end. And then the server has to basically ask the client, what did you do last time you were here, and then respond accordingly rather than maintaining the state on their end. So cookies are a great solution to the problem that they solve, which is allowing clients to have some state with the server while the server doesn't have to do any work to do so. And the server doesn't have to remember anything about the client. Now, if you want a fresh version of balloons.com, all you have to do is not send your cookie, so clear out your cookie cache or simply not send it. And if you have multiple things in your cart, you may end up with either a longer cookie, so perhaps the developer bakes it into the same string. They have it as like bal1, bal2, bal3. Or maybe they have multiple cookies, so for every item you add to your cart, it makes a new cookie. There are all kinds of different approaches to using those cookies, just like any other conditional in programming. Before we move on to caching, let me talk about third-party cookies. So the difference between a first-party cookie and a third-party cookie is that a third-party cookie provides you a cookie for a different website. So let's say you're on balloons.com, and balloons.com responds with a cookie for helium.com. And next time you visit helium.com, your browser searches its box of cookies and provides that one to helium.com. What's the significance of that? Well, the original intent was for something like, let's say balloons.com has a partnership with helium.com, and they want to offer you a coupon code. And they want to offer it to you without you having to type it in. So they would simply give you this cookie, and when you visit helium.com, you'll serve it, and helium.com will note that you were a visitor of balloons.com and you're eligible for their discount. That's a legitimate use of third-party cookies. In practice, what they're typically used for is advertising and advertising redemption. So when you visit balloons.com, your browser is going to send all of the cookies that it has for balloons.com. And that allows balloons.com to tell actually where it is that you were first exposed to their website. Where did you see an ad for it? Because when an advertisement is served to you, what it will often do is leave a cookie for the website that it's advertising for. So if you see an ad on, let's say, YouTube for balloons.com, it will leave you a cookie showing that I saw an ad on YouTube for balloons.com. And then when you visit balloons.com and redeem that cookie, balloons.com knows that they got your business because you saw an ad on YouTube. Even if you didn't click it, even if you went through and watched your video normally, that third-party cookie will come in when you ultimately do visit balloons.com. They can have a full reference of all the different times that you were exposed to their advertising. So some people find this annoying and turn off third-party cookies. But again, there are a lot of legitimate uses of third-party cookies when different web pages have to communicate with one another. It is very restrictive to only be able to set cookies for the page that you're on, especially when different services actually are connected. Like especially government web pages tend to redirect you to other URLs, and those would be third parties as far as cookies are concerned. So it's a bit of an issue. It's difficult to avoid getting tracked by those advertiser cookies. There are also more nefarious implementations yet of different social media platforms and such forming whole profiles of you by sending you a lot of cookies. Facebook is a pretty big sender of cookies. They will basically track many of the sites that you visit by providing you Facebook cookies, and then next time you visit Facebook, you redeem them. They see a list of all the different sites you visited that have the plugin enabled, so they have this sort of system to track you as well. So that's the darker side of cookies. Alright, let's go on to web caching. Caching is used to save bandwidth across the internet, make requests fulfill faster. You've probably heard caching in other contexts as a high priority storage for something else, so for example your CPU cache or your RAM, etc. The caching is the more limited but quicker to respond storage, and then you've got your low priority, long to respond storage. Most of your web browsers have a cache built in, and this is basically just a list of things that I've already gotten. So you cache the websites that you visit the most frequently. When you visit a service on the internet and you make a request to it, your browser will check if it already has it in its cache. And if it doesn't, then it will request it directly from the host. Otherwise, it can serve you that file directly from cache. Now, a lot of browsers will not serve you the file that they have from cache if they're not able to make contact with the host, so as not to basically deceive you. And a lot of modern browsers just don't have a real cache enabled at all. They just cache a small amount of resources. Helps to save space too. But you can usually enable some form of web caching in your modern browser, and it does help speed up your internet experience if you're on very limited internet and you tend to visit the same websites. So how does the browser know that the resource that it's requesting is still up to date? Let's think back to all of those different headers that we saw. How does the browser know that the resource is still up to date? Which one might it use? Anyone remember the different headers we looked at? Which one might be used to check if a resource is still up to date? I'll spoil it because I'm sure no one remembers the headers. There is this date modified, if modified since field that we can use. So cached resources, when they're stored in the browser's cache or in any web cache, they're stored with a date modified header, and this is basically the last time the browser or the cache got that resource. So they remember, what was the last time I got this resource? When the browser wants to check if there's a new version of it available, so let's take Google as an example. Google's logo changes daily, right? So if your browser has the old version of Google's logo, it's going to have it stored with an older date modified. So let's say you visit it on Thursday. It stores it with a date modified of Thursday at 2 p.m. Now you go and visit Google again on Friday. It tries to get the logo, so logo.png or whatever it is. It's going to make a request to the service with a conditional get, and it's going to provide its if modified since date as what it has stored, so Thursday at 2 p.m. So it's going to be a conditional get if modified since Thursday 2 p.m. If the Google logo hasn't updated, if it was the same on Friday as it was on Thursday, then the server will respond with a 304 not modified, which contains no payload, so you don't have to send the payload, saving a bit of traffic, and the browser knows that it doesn't have to update its cache. And it can serve the client with the version that it already has cached. If it gets a response, then it knows that it does need to update it, and it will update its cache and update what it gives to the final client as well. So basically getting a 304 not modified means you have the most up-to-date version, whereas getting an actual response means that you do not have the most up-to-date version, and now you do, and now you would update your date modified header again, and now you would have the most recent version again. So some caches will only check for new resources so often, so they'll not do any kind of GET request for some time. Some will do it every time but serve the client right away and then make the change as needed. There are many different approaches to how you can get your cache to work. All have advantages and disadvantages. But of course, if you're waiting for the response on a conditional GET, you're not really doing much in terms of helping with delay. So waiting for the response is probably not the optimal way to do it. Let's say you're at a large institution. Large institutions, any kind of big organization, will often maintain a cache of all the common resources that they use. Organizations like, let's say, John Carroll have a lot of internal website products like Banner and these kinds of different things that we use internally that all of our different people on campus probably visit fairly often. So we likely have a cache of common resources somewhere on a local server. This has become a less popular practice as the internet has gotten faster, and this has become less important and less of an advantage. So you don't often see these anymore just because internet requests go through so quickly anyway. But you'll still see them in places where the internet is very slow or bandwidth is limited for other reasons. This is often called a web proxy or a web proxy server. Whenever anybody on the network, on that network, so again, let's use John Carroll as an example, whenever anybody on campus makes a request on the internet, it asks the cache first for those resources. So this adds an intermediary between you and the internet. And if the cache doesn't have the resource, then the cache fetches it for you and then gives it to you. And it might also add that resource to its storage if it thinks that other people will use it in the future. So this adds a bit of a delay in the worst case because you're not speaking directly to the resource, you're speaking to the cache first. You also have to account for the delay of that communication on top of the delay with the resource itself, and then whatever handshakes have to happen and all that and so forth. So this actually adds some delay whenever there's a cache miss, so whenever there's something that's not inside of the cache. Your ISP, your internet service provider, also configures loads of caches for you. They configure something like a web proxy on your behalf. They will basically make complete copies of popular web pages and their content. So, for example, YouTube, Netflix, the different video streaming platforms, it would be bad for your ISP if all of that traffic had to travel over their entire network, because then they have to account for a lot more bandwidth. The easiest way for your service provider to serve you Netflix is to configure peering with Netflix on a node that's near to you. So basically, every ISP has a bunch of regional Netflix nodes that are complete copies of Netflix, and I'm just using Netflix as an example. Any of the other large streaming platforms have the same experience. So let's say maybe Ohio, maybe even our county has a complete copy of the web page on some server here for probably any given ISP. So all the ISPs in the area, WOW and Spectrum and AT&T, they all probably have their own copy. And anytime you make a request to Netflix, instead of going to the version of it, the web page that's far away in New York or wherever, your browser connects directly to the local cache of it and downloads the data there. And now your service provider doesn't have to worry about sending you all of that video data, that big, heavy video data, all the way from New York or wherever the original server is. It only has to worry about sending it to you from a nearby area, which means less fiber for them to run, less work for them to do, more money for them to make. So ISPs will cache popular web pages and their content for free. They will actually, nobody will pay typically in this relationship. The ISP will provide the cache for free, and Netflix or whoever will provide them the resources they need to build it for free. Sometimes the relationship is that the website, the popular website, actually buys the infrastructure and gives it to the ISP. So Netflix has this program where they will actually help you build the infrastructure to cache their website. That's why I mentioned Netflix as an example. So if you're a smaller service provider, Netflix will actually, for free, give you the cache so that customers on your service provider have a better Netflix experience, as in the page responds faster, and you're more likely to get those high bandwidth 4K videos and such served to you more easily when the internet is otherwise busy. But you can also typically buy cache space at the internet service provider level, which makes a a very interesting question from an economic point of view is how do you enter the market at this point if you are a competitor to Netflix? So if you want to start a competing service to Netflix, and Netflix has caches all across the country and you don't, your service will be slower. Obviously, your service will be slower. That's why competitors have to have a pretty hefty war chest in order to get started, because in order for them to have a similar experience, they're going to have to buy cache space at the ISP level all around the country to improve the response time to their web page too. And that's why you typically don't see a ton of competition once different services like that become more embedded, and so why it's very difficult to compete with those services today. Alright, we will resume this discussion next time. If anybody's interested, or maybe even if you're not, I'll upload the cheating client for that homework. I'm not going to update the server's side for the mitigations, I don't think, unless anybody requests it. Alright, that's it for today. See you guys on Friday, and then enjoy your Thanksgiving break. One more day. Woo.